All right, let's look. So differential equations all day today. Differential equations. And in my mind, there's maybe like kind of three-ish variety of things we talk about with differential equations. That's probably a low end there. But the first thing we typically like to kind of talk about is just showing something as a solution to a differential equation. So for example, I want to show or verify that the following solution, y equal to 5e to the negative 3t plus 4e to the 2t is a solution to the differential equation y double prime plus y prime minus 6y is equal to 0. For most, gosh, why won't that thing disappear? Sometimes it just goes away. It really bothers me that it just doesn't want to go away. I know it's not a big deal, but it bothers me. I'll just live with it. Fine. Okay. So when you're asked to do something like this, there's usually kind of one of two ways this goes. Most of the time, it's take the solution that they've given you, find all the necessary functions and derivatives of it. So here, since I've got a y double prime and a y prime, I need the first and second derivative to help me out here. So first we're going to find y prime. We're just taking derivatives. So the derivative of 5e to the negative 3t is going to be 5e to the negative 3t times negative 3, which is negative 15e to the negative 3t. And the derivative of 4e to the 2t is going to be 8e to the 2t. And I'm going to find the second derivative. Second derivative is going to be, well, negative 15 times negative 3 is 45e to the negative 3t. And 8 times 2 is 16e to the 2t. If we're verifying this, we shouldn't plug it in and just say it's equal to 0. We should plug it in and then simplify it until we actually get it equal to 0. So let's do that. So now we're going to plug in. So plug in what we've got to the differential equation. So plug into the differential equation. All right, let me ask you all. I know this might not seem like a hard question, but I'm asking anyway. Which of these is the differential equation? The y equals 5e to the negative 3t plus 4e to the 2t, or the y double prime plus y prime minus 6y equals 0? Which one is it? The first one or the second one? The second one, right? The one with the derivatives is the one that's the differential equation. The one that's y equal to some stuff is the solution or the function. So we're going to plug into the differential equation. We're going to get, all right, I'm just going to throw in y double prime. So instead of y double prime plus y prime minus 6y, now I'm going to get y double prime, which is 45e to the negative 3t plus 16e to the 2t plus y prime, which is negative 15e to the negative 3t plus 8e to the 2t minus 6 times, well, I don't have enough room here, barely. Minus 6 times y, which is 5e to the negative 3t plus 4e to the 2t. Now, if you're trying to like do this on a test and get away with not showing a lot of work, you can probably just, as long as you've done everything right so far, just say it's equal to 0 and be done with it. But what you should do is actually group all the things together. So I have a 45e to the 3t, sorry, e to the negative 3t, plus a minus, so minus 15e to the negative 3t, minus 6 times 5 is minus 30e to the negative 3t. I'm kind of thinking of all those as one part, plus a 16e to the 2t, plus an 8e to the 2t, minus 6 times 4 is minus 24e to the 2t. And notably, 45 minus 15 minus 30 is 0. And 16 plus 8 minus 24 is 0. Oh, it's 0, as it should equal 0. So that's the idea. When you're verifying something's a solution to a differential equation, you're taking the answer they've given you, taking whatever derivatives you need, plugging them into the thing that's the differential equation, and then seeing that you actually get what it's supposed to be equal to. Let me see if I have the other variety. Yeah, there is another variety of this, which I should show you. So questions about this before we do another one? Yeah.
Sorry. In the 45 e to the 3t.
E to the negative 3t.
Negative 3t, yeah. What is that? Is that a minus sign?
Right here?
Yeah.
So
Yeah.
like here, that is a minus sign there. Sorry, I know. Sometimes my penmanship is less than amazing. Yeah. So 40. So really, I'm saying 45 minus 15 minus 30 is 0. Right. I could have written this as 0 times e to the negative 3t plus 0 times e to the 2t, but this seems unnecessary. Okay. Let's look at kind of another verify one, but it's a little bit different. Or at least it's a little bit different in my mind. So let's see if I can keep numbering things. So verify that x cubed plus y squared plus, not plus, equals a constant times y is the general solution. It's general because there's a constant of like we didn't pick a number for it to the differential equation y prime equal to 3x squared y divided by x cubed minus y squared. Minus y squared, that seems dicey. Okay, so when you look at this, they didn't give us y equals a function of x to differentiate and solve for. And although you might be able to solve for y here and differentiate it, that's really not the way I would recommend doing this. Yeah, people do all sorts of weird things here. Here's what I normally do. I take this equation to start with the x cubed plus y squared equal to cy. Remind yourself that y is a function of x, right? We are at least pretending that y depends on whatever the other variable is, x or t typically. Now we're going to differentiate both sides. But I just said something important, that y is a function of x. So when we take the derivative of something like y squared, it's not just going to be 2y, it's going to be 2y times the derivative of the inside stuff, which is dy dx or y prime. So basically differentiate both sides implicitly, like we did back in 17a. So the derivative of x cubed is 3x squared. The derivative of y squared is 2y times y prime. And the derivative of a constant times y, the constant hangs out, and the derivative of y is the derivative of y prime, or dy dx if you prefer. Okay, I'm really not feeling good about this. I'm going to be perfectly frank. This doesn't look good to me so far. Maybe it is a mistake, to be honest. I don't think this is a mistake because this is a problem like from a worksheet I've handed out many times, but I'm not feeling excellent. So I'm trying to get from here to there, right? Because I started with the solution. I'm trying to show it actually means the same thing as the differential equation. So I'm going to try and solve this for y prime. I think, yeah, I guess so. So solve for y prime. I will point out a lot of these problems are kind of like do what you can. So if I solve for y prime, I would say that 3x squared is equal to c times y prime, bless you, minus 2y times y prime. Factor out the y prime. So 3x squared is equal to y prime times c minus 2y. Solve for y prime. The y prime is going to equal 3x squared over c minus 2y. Okay, now we try to see what do I need to do to this to get to that. Well, let's see. I've got 3x squared over c minus 2y, and I really wish I had a 3x squared times y on top. Well, I can make that happen. I'm allowed to multiply the top and bottom by whatever I want. So I'm going to take my y prime equal to 3x squared over c minus 2y and multiply the top and bottom by y. On top, I'm going to have now what I want, 3x squared times y. And if I distribute the y on the bottom, I'm going to have cy minus 2y. And now here's where I feel like is the tricky part. C times y is not part of my answer. Right? I don't have a C times y anywhere in the bottom there. That's not what I'm looking for. But if I look at my original equation, that's supposed to be my solution. C times y is equal to x cubed plus y squared. And that still feels bad. Oh, I made a small mistake. Y should distribute to both of those terms. Y times C is CY. Y times 2y is 2y squared. Okay, I was worried for a minute there. So then if I replace CY with the thing that it's equal to, I get that y prime is equal to 3x squared y over cy, which is x cubed plus y squared minus 2y squared. And then that does get me to say that y prime is equal to 3x squared y divided by x cubed, and y squared minus 2y squared is minus y squared. I will certainly say that when you have one like this, where you're not starting off with y explicitly as a function of x, it's a little bit more work. It's a lot more work, actually, to be honest. And there are other ways of doing this. This is the way I think about it because it's just the way I think about it. That doesn't mean it's necessarily the rightest way to do it. There might be other ways of doing this that are better. I'm just not good at seeing them. It's probably, no, I don't want to say that. There are probably other things you could do here that might have been an easier way to get there. I'm not good at seeing them. Good question. When I got to here, why did I multiply by y over y? Say that one more time. Right, because I knew that I wanted this. I was trying to show that if I start with the solution, I will get the differential equation. That y prime is equal to 3x squared over c minus 2y. Oh, sorry. The y prime is equal to 3x squared y over x cubed minus y squared. So I said, well, I need a y on top. But if I can't just multiply by y on top, I have to multiply by y on top and y on the bottom. So I did the thing that would help me get to a place where the solution I was getting looked more like the thing I was starting with.
Where did the 2y squared, the negative 2y squared go?
So from here to here? No. From there to there, what's y squared minus 2y squared? Or let me say it this way. What's 1y squared minus 2y squared? Negative 1y squared. Right there. Yeah. Yeah. I think, yeah, let's leave it there. I should say other questions about this. Again, I like the other variety better. They feel a little more straightforward, but sometimes you are faced with something like this. The thing to look for here is the word verify or confirm that this thing is a solution to this other thing. You're not being asked to solve the differential equation, which is what's coming up next. You're just being asked to show that this thing is a solution. Before we start solving them, let's look at one other thing. So sometimes, grab the notes here. Yeah. We might like to visualize some solutions to differential equations. For example, and this is where we get to the, oh gosh, what are they called? Giant brain. Yeah. The phase plots and the phase lines. Let's talk about the phase lines first. So sometimes it is useful when you have an autonomous differential equation. I know I said I didn't really care about those words, but I'm going to say them because your teachers might be saying. So an autonomous differential equation, which is where you have the derivative depending only on the dependent variable y. So your derivative dy dt is a function of y, or you might write y prime is some function of y. Let's look at an example that we're not going to solve. So here is an example of an autonomous differential equation. Dy dt is equal to, let's make it easy, 3 minus y times, sure, 1 minus y. Or you could multiply it out, right? That's equal to dy dt. I don't really want to multiply that, but it's y squared minus 4y plus 3. I don't know what the solution to this looks like. It would be doable. You could actually solve this using partial fractions. It's not particularly nice, but we're not really caring about that just yet. I want to see how this thing looks. What I really want to see is, where are there points of stability? So when we say the word stability, what do we really mean? Well, I would say that this function y is stable if it's not changing. If something isn't changing, its derivative is 0. So a differential equation has critical points. I'm not going to say they're stable just yet, but we have critical points wherever the derivative is equal to 0. So our critical points, well, we already know what the derivative is. The derivative is dy dt. So the critical points are exactly when dy dt, which in this case is equal to 3 minus y times 1 minus y, is equal to 0. So our critical points are where y is equal to 1 and y is equal to 3. To determine whether they are stable or unstable, or I guess semi-stable is also what people talk about, we graph this thing. So what we do is, I'm really going to think of graphing, like I'm thinking of this kind of like, I know it's a terrible thing. I'm thinking of this is like my y. And this is like my 3 minus x times 1 minus x. I'm still going to graph it using the right names, but really we're just graphing in the usual way. We know how to graph a parabola, x squared minus 4x plus 3. So there's my x-axis, there's my y-axis. I'm going to label them other things. If I plot this thing, if I graph this thing, well, my intercepts on the horizontal axis are just going to be 1 and 3. All right, which way is my parabola opening? Good question. Up or down? Well, if we look at the way we multiplied it out here, it's definitely up, right? My leading coefficient there is a positive thing. So it's looking kind of like this. We should label these axes the correct way. So this horizontal axis is the y-axis. And this vertical axis is the y prime axis. Now, one of these is stable and one of them isn't. Not because that's how it always works, but because one of them is going from positive to negative and one of them is going from negative to positive. So this is the thing that I think people actually, most teachers really like this for some reason. I kind of like it too, I'm not gonna lie. It's interesting. But I'd be willing to bet most people will ask a question about this on one of their exams. So which of these is stable? Well, here's the deal. To the left of 1, so if y is less than 1, y prime is positive. If y prime is positive, that means y is increasing or decreasing if the derivative is positive. Y is increasing. So over here, when y is less than 1, y is getting bigger. Over here, between 1 and 3, the derivative is negative. So if y is between 1 and 3, the derivative, or I should say y, is going to get smaller. Similarly, if y is bigger than 3, the derivative is positive, so the y's are increasing. So what happens here is if you start at say like y equal to 4, this function is just going to get larger and larger and larger because the rate of change, the derivative is going to be positive, the function is going to increase in value forever and ever and ever. If you start between 1 and 3, you're going to get pushed towards 1. But then if you end up on the other side of 1, you're going to get pushed back towards 1. So this function, I would say that y equal to 1 is a stable critical point. Y equal to 3 is unstable. And really, if you draw this phase line, you're going to get stability if you're from left to right, your function goes from positive to negative. You're going to get instability if you go from negative to positive. And then it's semi-stable if like you stay on the same side, which is super annoying and we shouldn't really talk about. But that's kind of the gist of this thing is you draw the graph of it and then you just kind of see, okay, well, if my arrows are pointing towards the point, it's stable. If my arrows are pointing away from the point, it's unstable. Why are my arrows pointing to the right this way? Because my function's positive. Why are they pointing to the left here? Because it's negative, right? Because it's positive. Yeah, we should talk about the other thing is less fun to talk about, but we should talk about the other thing. So phase plots, on the other hand, are something you probably won't have to do much of, but you might be asked to look at. So a phase plot, first, let's make something up. I've got something like dy dt is equal to, how terrible do I want this to be? Not that terrible. Let's say it's y minus t. Non-autonomous, right? It's not pure time. The derivative doesn't just depend on time, and it's not autonomous because it doesn't just depend on y, it depends on both. So it's non-autonomous. Not that you need to know that really, but that's not true. You should be able to recognize that with some practice. I will mention here, we can't really draw the thing that we did before, right? Because unlike the previous one, this is not just a function of y. So we can't do y prime on the vertical axis and y on the horizontal axis. But we can draw this phase plot, which we'll do once, and you'll all see how terrible it is. And then maybe we'll talk about something else. Let's talk about how you draw this. So yeah. All right. So here's the idea. You're gonna pick a bunch of points, which is why this is annoying, and you're going to see what the derivative looks like. So for example, if let's not start at 0, 0, because that's terrible. If t is 1 and y is 0, my derivative is 0 minus 1, which is negative 1. So the slope of my tangent line at that point, so I'm going to draw like in red here, is a slope of negative 1, like that. And if I go over to, let's say, 2, 0, my slope is negative 2. For the same reason, 0 minus 2. Steeper. It might be better to go in a different direction. So often it's not a bad idea to kind of see what curves make the derivative some constant value. So for example, if we want dy dt to equal 0, we need y minus t to equal 0, or y equal to t. T, that's not a t. Let's make it a t. There, now it's a t. So along the line y equal to t, all of my derivatives are 0, which means all my tangent lines are horizontal. So for example, at the point 1, 1, at the point 2, 2, at the point negative 1, negative 1, point negative 2, negative 2, all of my tangent lines would be a little horizontal tangent line. And I might continue in this way. I might say, well, okay, what if we want y minus t to equal 0? I'm sorry, that's what I just did. Y minus t to equal 1. Well, that's y equal to t plus 1. So I'm just shifting things up by 1. So along the line, y equal to t plus 1, which is everything like on this line here, all of my slopes are going to be positive 1 because I'm setting my derivative equal to positive 1. So at the point 0, 1, my slope is 1. At the point 1, 2, my slope is 1. At the point 2, 3, this should all be pointing in the same direction. 1, like that. Over here, 1. Over there, 1. This is not a particularly efficient thing to do, right? This is very like unwieldy, and there's not really a great way to do this by hand, which is why people don't do it by hand. But occasionally you might be asked to look at something like this and kind of say things about it. Let's look at a couple more just to kind of fill this out a little bit more. If I wanted dy dt to be the constant value of 2, well, I'd have y equal to t plus 2. So again, I'm just shifting up 1. So along this kind of line here, all my slopes of my tangent line should be +2, so even steeper. And we can continue in this way. Over here, there'd be -1. Further down, there'd be -2. And so you've kind of got this behavior where if you say, okay, great, well, James, what happens if you start like right here? Well, you can kind of start following the pattern of the curves and see that it's going to do something like that, which seems kind of bonkers. The reason I'm mentioning this is because sometimes people are going to show you graphs like this and kind of ask you to say, well, what happens if we say, for example, given an initial value of, say, y equal to 2 and t equal to 4, draw the curve, the solution curve. Sorry, I'm like, I knew there was a word I was missing there. Okay, so if we go over to the point where t is 4 and y is 2, which I know we haven't plotted yet. Let's see, so if t is 4 and y is 2, we're going to have a slope of -2. So we're already starting very negatively. And if we travel in that direction, well, we're going to end up being even more steep. And so we're going to kind of go this way and just kind of go down, 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 down like that. I'm probably not doing the best job ever of explaining it because it's still something that doesn't always completely gel very well in my brain, to be perfectly frank. But that's the idea, is this phase plot represents all the possible solutions to this differential equation. And we could solve this differential equation after a little bit. Like, we can't solve it right now because we still need to talk about how you solve it. But once we see how to solve it, the solution will be some sort of solution where there's a constant in there. And then depending on the constant, you might get this curve or this curve or this curve or this curve, depending on which constant we're saying we're starting with. Let's hold off though. So we're going to come back. I promise you we will come back to this when it makes a little bit more sense after we talk a little bit about how to solve differential equations. And I will mention that there are probably 3 broad categories of differential equations that we're going to solve in this class. One example is ones you already know how to do. Here's a differential equation. It's not the pen I want. Solving differential equations. So here's a differential equation. dy dt equals 2t e to the negative t squared. So the derivative is some function of t. If I want to solve the function for the function y of t, I'm just going to take the antiderivative. So I want to solve this differential equation. The solution is that y as a function of t is equal to the antiderivative of 2t e to the negative t squared. Which we could not too difficultly integrate. I would probably do a u sub here, let u equal -t squared. Du is -2t dt. Negative du is +2t dt. So that's going to equal the integral of -du e to the u. You end up with -e to the u plus c, which is -e to the negative t squared plus c. So y of t equal to -e to the negative t squared plus c is the general solution. General because we haven't said what c needs to be, right? It could be this for whatever value, is the general solution to the differential equation that we just talked about. dy dt equal to 2t e to the negative t squared. So if they're just telling you that the derivative is a function of whatever your independent variable is, the solution to your differential equation is just the usual process of finding the antiderivative. Let's look at another example like that. if I can move the page. Let's say we have the following. So given the differential equation, sure, dy dx is equal to, yeah, let's not say, let's say secant squared of x minus cosine of x plus 1. And y of 0 is equal to, that's not very exciting, but fine, is equal to 4. Find the particular solution. The only difference between a general solution and a particular solution is that for the particular solution, you have to use whatever initial condition they've given you, in this case, y of 0 equals 4, to figure out what the C constant is. Same process though here. So we've already got dy dx in terms of just x, so there's nothing else to do but anti-differentiate. Usually it's not going to be that easy, but it's good to start off with ones that are that easy. So we're going to find, I like to write y of x or y of t or y of whatever my independent variable is, just to be extra clear. That's going to be the antiderivative of secant squared of x minus cosine of x plus 1 dx. And we can definitely integrate that. The antiderivative of secant squared is tangent of x. The antiderivative of negative cosine is negative sine. Plus x plus c. I didn't mean to pick ones that worked out this way, but I happened to pick ones that worked out this way. So now I'm going to plug in. So I'm going to plug in 0 for x. Y of 0 is tangent of 0 minus sine of 0 plus 0 plus c equal to 4. And I'm saying equal to 4, right? Because if x is 0, y is 4. That's what this says over here. And then, unexcitingly, tangent of 0 is 0. Sine of 0 is 0. So you just end up getting c. Usually it's a little bit more interesting than that. Like usually you have to actually do some adding or subtracting to find c. But here we get c equal to 4. I want to stress a lot. We're not done. We didn't finish the problem. We didn't answer the question. Because the question said, find the particular solution to this differential equation, which means we have to write the function again with the constant value plugged in that we actually have. So our actual solution here is going to be that y as a function of x is equal to tangent of x minus sine of x plus 4. To be vigilant, whenever you're finding the solution to a differential equation, the solution is a function of whatever your independent variable is, t or x typically, but really could be anything. They get more interesting. So there are 2 other varieties of differential equation that we typically solve in this course. The easier ones are what are called separable differential equations. Separable differential equations. For example, I don't want to start with that. Sure, let's start off with something like paper. Oh, this is the same. Is it the same? Okay. Sorry. I'll just make something up. Something like x cubed times dy dx equal to, let's not get too crazy here, James, y plus 1 squared. This is separable because if you isolate dy dx, you can write the other side as a function of x times a function of y. Or really, as I would encourage you to think of it, actually, you can pull all of the y things to one side and all the x things to the other side. If it's written in the usual way, meaning someone wrote it with dy dx on the left-hand side, that's just the normal way of writing it. It means you want to pull all the y's to the left and all the x's to the right. Because we want the d whatevers the dy and the dx to never be in the bottom. So I'm going to pull the dx over there, and then I'm going to also divide by x cubed and divide by y plus 1 squared. So let's check this out. So solving here, or I should say separating variables, we have dy dx equal to y plus 1 squared over x cubed. And then I'm going to bring the dx up there and the y plus 1 squared down there. So 1 over y plus 1 squared times dy equals 1 over x cubed times dx. Now it is separated. Not every differential equation, not even most differential equations are separable. I just want to point out really quickly here, dy dx equal to something super simple like x plus y is not separable. There is no way that you can have a function of x times dx equal to a function of y times dy here. Because the multiplication and division are really the only things we're allowed to use here. There isn't a way to bring dx over there and get it not attached to the y. Can't be done. Not every equation, not most equations are separable. This one is though. So now, once you've separated things, we can anti-differentiate both sides. So the integral of, I might write this as y plus 1 to the negative 2 dy equal to the integral of x to the negative third dx. And now we're going to anti-differentiate. I think you can get away without doing a u sub here and just saying the antiderivative is going to be y plus 1 to the negative 1 over negative 1 equals x to the negative 2 over negative 2 plus c. Why not plus c on both sides? Because we're lazy. And really what we did is we said this was plus c1, this was plus c2, and then we subtracted c1 from both sides to say that this new c is c2 minus c1. So really it's totally legit. We're just skipping that step and saying, always put the c on the side that doesn't have y on it. Because if we can, we would like to solve for y as a function of x. So that's what we're going to do. Yeah, is that what we're going to do? Maybe. So let's see what we've got here. So simplifying this a bit so it looks less terrible, I've got a negative 1 over y plus 1 equal to negative 1 over 2x squared plus c. And I would like to solve for y. Yeesh. Okay, so let's do this. It's actually not that bad, but I want to point out a couple things that happen often. So I'm going to solve for y. I'm first going to multiply both sides by negative 1. Watch. I get 1 over y plus 1 equal to positive 1 over 2x squared plus a new constant that I'm going to call the same as my old constant. So even though these constants are actually different, no one cares. No one cares unless you actually have to find what the constant is, and then you at some point decide to actually find it and then keep track of things. But if you're just multiplying a constant by a constant, or adding a constant to a constant, or subtracting a constant from a constant, it still stays a constant. Some people keep track by saying, okay, well, this is like c sub 3, this is still c sub 3, and then I changed it, so now this is c sub 4. Really unnecessary. But if you like to do that, you are certainly welcome to do that. All right, solving for y. Now here's where things that are really not nice. I'm going to take the reciprocal of both sides. So I'm going to get y plus 1 equal to the reciprocal of this entire side. I can't just flip each thing individually. It's really going to be 1 over all of that grossness. And there you can't just say the c like stays off to the side. You really do have to put it there. And then finally, we subtract 1 from both sides. And our solution, y as a function of x, would equal 1 over 2x squared plus c minus 1. And that would be the general solution to this separable differential equation. There's probably nicer ways to write it. We're not so concerned with that right now. I wouldn't check, but you could check. You could take the derivative of this, multiply it by x cubed, and then show that it's equal to this thing plus 1 squared. It's kind of neat, but it's not super necessary. Questions?
How come we have the C under
Good
the
question. So the reason we have this is because
yeah.
when we're solving for y here, basically what I've done is I've taken the reciprocal of both sides. So what I've really got here, in fact, let me show another way of doing this. So I've got 1 over y plus 1 equal to 1 over 2x squared plus c. And I'm trying to solve for y plus 1. So what I'm really going to do is I'm actually going to multiply both sides by y plus 1. So 1 is equal to all this stuff, 1 over 2x squared plus c times y plus 1. And now if I'm trying to solve for y, I'm going to divide both sides by all this. So 1 over all of that plus c is equal to y plus 1. And then if I subtract 1 from both sides, I end up over here. So that's why we end up with all that in the denominator, because you can't, when you take the reciprocal of both sides or try to get something out of the denominator, you have to do it to the entire side as one kind of thing. You can't do it piece by piece.
That makes sense. It's just earlier you said that C would represent a constant either way, and
Right.
the reciprocal of C would still be C. So I guess I'm kind of just not understanding why this is like the exception.
Well, so what I would say is the things that don't really affect C are if you add, subtract, multiply, or divide by another constant. But here you're inverting the entire expression as opposed to just each thing piece by piece. Let me do another example, and we'll kind of talk about how things with C work. But the idea really is, like, because this value here is some constant here, if I'm taking the reciprocal of this side, I can't just say it's the reciprocal of this plus the reciprocal of this, because if this had been 4 and then I add it here, the reciprocal is different than if I take the reciprocal of 4 and then add it to the other thing. I know I'm kind of just saying the same thing over and over again. So let's do another example. We'll try to see a little bit better how that works. Let's see here. So let's say we have something like dy dt, sure, equal to y times x plus 3 squared. And in addition to, it's terrible. It's not that terrible, but I said dy dt equals y times x plus 3 squared. I should have said t plus 3 squared. Sorry about that. And let's say that we know that when I don't really want to say yet, but we'll fix it if we have to. Let's say that y of 0 is equal to 5, which will allow us to solve for c. So let's go ahead and do the thing. So we're going to separate. So 1 over y dy is equal to t plus 3 squared dt. And we're going to anti-differentiate both sides. You totally could multiply out the right-hand side as t squared plus 6t plus 9 and anti-differentiate that way, but I think we can just anti-differentiate this as it is. Integral of 1 over y is the natural log of the absolute value of y. Integral of t plus 3 squared is t plus 3 cubed divided by 3 plus c. And yes, that should work out just fine. Cool, yeah, okay. So the good / bad news is you can kind of find C whenever you want. Usually there is a best moment to find C. So I could find C right now. I don't really want to though, but I could. So I could find C right now and say, okay, well, if y equals 5, t equals 0, I really should say if t equals 0, y equals 5. If I plug that in, the natural log of 5 equals 0 plus 3 cubed over 3 plus c. And then the natural log of 5 is equal to, let's see, 3 cubed is 27 divided by 3 is 9. So c is equal to the natural log of 5 minus 9. The problem with doing it right now is now when I try and solve for y, I have to carry that with me the whole way. And I can't just say a constant times a new constant, I have to actually track the value. But let's watch. And we'll do it twice because I think it's worthwhile. So the natural log of the absolute value of y is equal to t plus 3 cubed over 3 plus the natural log of 5 minus 9. Gross. Now let's try and solve for y. So we're going to do e to the on both sides. All right, so e to the natural log of the absolute value of y is the absolute value of y. I'm going to get e to the that. So e to the t plus 3 cubed over 3 times e to the that times e to the that. Right, and you have e to the something plus something plus something. We usually break it up as e to the something times e to the something times e to the something. Okay, so then I'm going to drop my absolute value here because I know that when t is 0, y should be positive 5. Right, so it's okay, right? If I plug in 0 here, I get 0. I actually get e to the 9, e to the negative 9, e to the natural log of 5, which is 5. So I'm okay to drop the absolute value here. It'd be different if y was supposed to be negative 5, then I'd have to like change the signs and stuff, but I'm not going to sweat it. So y equals e to the t plus 3 cubed over 3 times e to the natural log of 5 is 5 times e to the negative 9. And that's kind of our solution. It looks gross. We can make it look a little bit nicer. It's e to the t plus 3 cubed over 3 minus 9 times 5. I don't love that. Right, I picked the wrong moment to find c. I had to do way more algebra than I needed to. So let's do this again and be a little bit wiser about when we're going to try and actually plug in our initial conditions to find our constant. So instead, starting with the natural log of y equal to t plus 3 cubed over 3 plus c, and knowing that t equals 0 and y equals 5, let's do this. Let's just solve first. So we're going to e both sides. We're going to say e to the natural log of the absolute value of y is the absolute value of y equals e to the, still gross, t plus 3 cubed over 3 plus c. But that becomes the absolute value of y equal to e to the that times e to the c. And now I'm just going to call e to the c a new constant, a. So absolute value of y is equal to a times e to the t plus 3 cubed over 3. And now I can find this value of a with, I think, with less work. So I get y being 5, absolute value of 5 is 5, and t being 0. So a times e to the 0 plus 3 is 3, 3 cubed is 27, 27 divided by 3 is 9. So I can see that a is equal to 5 divided by e to the 9th, or 5 times e to the negative 9th. And then I can go back and say, okay, great. That means my solution here is going to be that value of a, 5 times e to the negative 9th, times e to the t plus 3 cubed over 3. And in my opinion, that's a lot less effort than doing all this and carrying that all the way. It's still getting the same answer. I know it looks slightly different because of how I've written it, but these answers are the same. E to the negative 9th times e to the t plus 3 cubed over 3 is the same as e to the t plus 3 cubed over 3 minus 9. So really, you kind of want to, if you have to solve for your constant, you kind of want to pick your moment, right? There is usually a best spot to be like, okay, I've got the constant thing kind of isolated, and if I did any more work, it would be less isolated. That's usually the time to be like, okay, I'm going to plug in my stuff now and try and find what C or A or whatever you're calling is equal to. Talk more about this on Wednesday. We'll talk more about separable equations. We'll also talk about the other kind, which are, I think, they're called first order linear differential equations. They might also be referred to as non-homogeneous differential equations.